Doug is.
Excellent, and we are live. So welcome everybody to part 2 of Google's QC Hack workshop. This will be a Cirq workshop. I wanted to give a disclaimer to y'all. This is a hands-on workshop. So Tanuj or Balint or one of us will post a link in the Twitch chat and you guys can follow along live. They'll also have breaks to check on how you're doing. So you guys can use Cirq and get really accustomed with the software. To introduce our 2 speakers today, we have Balint Pato and Tanuj Qatar. I'll introduce Balint first. Balint is a senior software engineer on the Google Quantum AI team with 15 years of software engineering experience. He got his Bachelor's of Science in Computer Science from ELTE Budapest, Hungary in 2010. He joined Google in 2017 and the Quantum AI team in 2020. He currently leads the development of Cirq, Google's open source quantum computing framework. And then for Tanuj, Tanuj is a software engineer on the Google AI Quantum team as well. He works primarily on Cirq, Google's open source quantum computing framework. Tanuj enjoys algorithmic problem solving. He has been a 2-time ACM ICPC world finalist and a 3-time trainer for the Indian IOI team. Prior to Quantum, he worked as a trader in an HFT firm and has also done multiple suite internships at Google and Facebook. So without further ado, Tanuj and Balint.
Thank you, Shion, for the great introduction. We do have an introduction slide ourselves as well. I'm Balint, and as Shion mentioned, I work on the Quantum AI team and lead the open source efforts with my main focus being Cirq. Outside of work, I enjoy doing a lot of things. During the pandemic, for example, I took hip hop dancing and Bhangra dancing classes with my wife. I also like surfing, making music, and also binging on terrible TV shows that I'm not even going to name. Cool, so let's see what we're gonna talk about today. I'm gonna keep it short with the slides. It's less than 10 minutes, a couple of quick slides around the NISQ era, what that means. And then Tanuj is going to talk for the first hour to get from qubits to simulation with Cirq. And then the second session, I'm going to talk about gates, parameterized circuits, devices, and compilation. It is inspiring to compare the current state of quantum computing to the early days of classical computing. Early digital computers were large, unreliable, and only had a few applications. However, they had a transformative impact across all industries and eventually all of humanity. What an amazing time to be alive, right? There are real quantum computers out there today. However, we have to know that they are severely limited. On this diagram, you can see how an actual quantum computation is being executed. On the backplane, we represent the initialization of an array of qubits that the quantum computer is operating on. Qubits are quantum versions of your well-known bit. A bit can be 0 or 1. A qubit can be in more complex states called superpositions, which we won't go into too much detail about. Thank you for the Microsoft team for giving an intro on quantum computing yesterday, and Doug's amazing presentation on quantum chess probably gave you a good intuition around it. And don't worry, you will be able to go through the workshop with a little Python knowledge and that background that you got from the other presentations. So the main axis is time, or circuit depth. And so we have 1 qubit, 2 qubit gates that are operating on the qubits, and then measurement gates at the end. So there's only so much space and time volume can be done before computation becomes lost to noise. So this is the problem, and this diagram is very, very illustrative in a sense that you can think of the computational volume being limited in near-term devices. As noise, interaction with the environment acts on the qubits, there is less and less information stored in the system, so the depth, aka the length of the computation, is limited. Also, building larger and larger systems is one of the hardest engineering challenges today. So that's why that axis is limited as well. The good news is that this volume has crossed over the capabilities of classical computers in 2019. The caveat here is that for only some specific niche tasks. So let's look at how these limitations in space and time volume impact applications. Looking at how the number of qubits influences the applicability of quantum computers, if you have up to 40 qubits, it is going to be easy to simulate them classically. Well, you need big machines, but you will be able to simulate them classically. It's also possible to simulate very noisy qubits. So when you have your limiting error rate here, this is the physical error rate, is too high, then you can still classically simulate quantum circuits. Given that our current devices are limited, it puts us currently in the blue region of noisy intermediate scale devices. So this is the NISQ era. And our research group has a two-pronged approach. One is interested in near-term applications, and the other one is interested in how we can get to the nice green area of error-corrected or fault-tolerant quantum computers. You probably heard about Peter Shor, the inventor of the quantum integer factoring algorithm, which is one of the first useful quantum algorithms that is exponentially faster, provenly, than its currently known best classical version. Well, that really requires a fault-tolerant quantum computer. So another result of Shor is that he's famous for is the threshold theorem, and that's what this dotted line is, and that's what we're talking about when we say error-corrected quantum computer or fault-tolerant quantum computing. So if you can push your physical qubits below this limit, there are certain error correction codes that can suppress the noise exponentially. And you will get, you can run as large quantum space volume as you want. Okay, so let's see the timeline. It is just natural to ask at this point, when are we going to get to error-corrected quantum computers? The simple answer is that we don't know. This is an area of active research. You can look at IBM, Google, and other companies' roadmaps, take them with a pinch of salt. They are estimates, and estimates go wrong all the time. There are still physics risks that need to be mitigated. However, there are good news. In 2019, we had the Beyond Classical Computing experiment that surpassed classical computing capabilities. Today is 2021, where we have early results around like single logical qubits, and so results pointing towards that direction. We are looking into the early applications like simulation, optimization, sampling, quantum neural networks in these early NISQ era devices. And then probably in 10 years, we'll get to the error-corrected quantum computer, which will unlock things like the unstructured search for Grover's algorithm or factoring with Shor's algorithm, and so on and so forth. So I just wanted to give a little anti-hype advisory here. We can hear a lot on the news about quantum computing, pop science articles that sound cool, private and public sector investments in building quantum computers. Some companies even claiming commercial value. And I just gave a couple of reasons to be excited. And it is okay to be excited. But in general, I would like to advise to hold next to the excitement space for be grounded in science, be skeptical, ask questions, look for caveats, and be prepared for risks, because the field is not yet established. So especially that you who are at the beginning of your careers, think about, be mindful about it and be excited. We want people who are talented, motivated, and with diverse backgrounds who will do the research, invent new applications, build scalable error-corrected quantum computers, but it's not there yet. All right, so with that out of the way, we're going to talk about Cirq today. Cirq is specifically meant for NISQ-era quantum computers. It allows you to use the gate model quantum computing language to define algorithms that can be run on current devices, a plethora of simulators, and you can express what operations should run in parallel on different qubits. You can have, that's the concept of moments that we're going to talk about. You can express device constraints and validate topology, supported gates, so validate circuits, whether they are according to a given topology or they have gates that are supported by the given runtime. And finally, it is built using the most popular scientific programming language today, Python. Cirq also became a centerpiece of Google's quantum open source ecosystem. Thus, starting to learn about Cirq will enable you to look into other projects as well, like Open Fermion for quantum chemistry, or TensorFlow Quantum for quantum machine learning. We are also keen on creating an open and inclusive community of contributors. So if you're interested in contributing, join us in our weekly Cirq sync. Give us a ping on Gitter if you have questions. And I put here the links for documentation as well on our new site in quantumai.google under Cirq. You will find every detail that you need. Obviously, everything always needs improvements, so improvements are welcome and contributions are welcome. So for the workshop, please use this link, and I'm going to hand it over to Tanuj at this point to kick off the first part of the workshop. And I'm going to paste this link into the chat.
Thank you, Valent, for an amazing introduction. Hi, everyone. My name is Tanuj. I'm also a software engineer at Google Quantum AI, and I'll be your host today for the first part of this workshop, where we will learn the basics of Cirq, write some quantum circuits, and also simulate them using Cirq's built-in simulators. So to get you all started, like we have pasted the links of this workshop or this collab in the description. Like you can also visit the quantumai.google/Cirq/tutorials website, and then find this tutorial under the educators workshop tab on the left side. So you should open Cirq intro workshop, and you should be able to see this page that I'm currently presenting. And once you get to this page, if you open, like if you click on run in Google Colab, it should open another window, which should look something like this. Okay. So I will take a break here for a minute or two and let everybody open this Colab in your local browsers. Again, like as we said earlier, that we want this workshop to be interactive and hands-on for all the learners. And this is also the first time we are trying an online hands-on workshop. So I'm super excited to see how it goes. And yeah, like if you have any questions or if you get stuck anywhere, please reach out in the comments. Like we will be constantly monitoring the comments. And yeah, like I'll take a break for a minute and let all of you open this page. Also, like once you get to this page, you can click on the top. If you are signed in on your Google account, like on your Gmail account, you can click on the top left and click on save a copy in Drive. This will create a local copy of this workshop, which you can then edit and also save in your Drive. So to give to give you guys a brief introduction, collabs are just Google's way of accessing Jupyter notebooks. So this is basically a Jupyter notebook which is running on cloud. So the Jupyter kernel is running on a Google hosted machine, and you can edit the collab on the web. Like you can save it, and you can also share it with your friends, just like you can share, say, Google Docs or Google Slides. So it is pretty convenient to write Jupyter notebooks using collabs. Okay, so I hope everybody has opened this collab by now, and probably also created a local copy if you are signed into your Google account. Okay, so let's maybe start with the workshop now. So like Valent has already introduced what Cirq is. So Cirq is basically Google's open source framework for writing quantum circuits for NISQ devices specifically. So if you come down in the first cell and try to run it, this should install Cirq on the machine on which this collab is hosted, and also import the library in this Jupyter notebook. So to run a cell, you can basically just go on the cell, click on it, and press Shift Enter. If you press Shift Enter on the cell, it will run the cell. So as you can see on my screen, it says installing Cirq. So it has downloaded Cirq. So it's basically doing a pip install, just like you would do on any Linux or Mac machine. And here we go. The Cirq library is now installed. We have also imported matplotlib and numpy, like just so that we can use them, like use these libraries in the exercises below. So now if you come down, you can see an image of Google's Bristlecone processor. Like this is an actual 72 qubit quantum processor that sits in our Santa Barbara lab. To make sure that we have imported the Cirq library correctly, we can come down and run this cell. So if you run this cell by pressing Shift Enter, it should print out the lattice of the Bristlecone device. So you see that I have said print circ.google.bristlecone. Bristlecone is a device in Cirq, and what you see in front of you is basically the lattice of this device. So therefore, which basically means that a set of qubits and the corresponding connectivity. So each of these tuples represent a qubit on the device, and the connectivity represents that which two qubits can have an operation, can be operated on together. So two qubits which are connected in this device can be operated on simultaneously. Okay, so this works fine. This means that we have installed Cirq and we have also imported it fine. So if you so now let's jump in on how we can create circuits in Cirq. So Cirq has these four main concepts called qubits, operations, moments, and circuits. So a circuit is basically an object which is a collection of moments. So the circuit object represents the quantum circuit that you want to write. A moment is an abstract time slice. So a moment in the circuit represents an abstract time slice. So you can imagine a moment as a layer of operations such that all of these operations can be applied during the same abstract time. And of course, because these operations can be applied simultaneously, these operations should also be applied on disjoint qubits, which means that in one particular moment, no two operations can be applied on the same qubit. Okay, so Cirq has this nice concept of moments, which lets you imagine your circuit as a layer of operations, where each layer is something where each layer represents a set of operations that can be applied simultaneously on your circuit. Okay, so an operation. Next, we have the operation. An operation is basically an effect that operates on a specific subset of qubits. This, the most common operation that we will see throughout this workshop would be a gate operation. And a gate operation just means that if you take a quantum gate and you apply it on a set of qubits, then it becomes a gate operation. There are also other types of operations in Cirq. For example, you have a global phase operation or a controlled operation, but we won't worry about them too much in this particular workshop. Okay, and in the end, qubits are the basic fundamental unit of quantum information. So if you look at this diagram below, you can see that qubits are represented by these horizontal lines. So each of these horizontal lines represents a qubit. Operations are represented by these boxes. So an operation can be applied on a single qubit, or an operation can be applied on 2 qubits, or an operation can also be applied on multiple qubits. And a moment is a layer of these operations. So a layer of operations which can be applied together. So you can imagine these vertical layers, and every layer represents a moment. And circuit finally is all of this combined. Okay, so this is a nice pictorial representation of how we represent qubits, moments, circuits, and operations in Cirq. Okay, so coming down, you can see a sample code which creates your first circuit. So if you just run this code using Shift Enter, you can see a nice ASCII diagram that gets printed out. So let's see what is happening in this circuit. Okay, so first we define 3 different qubits. We say A is equal to circ.named qubit A. So Cirq has different types of qubits. One of these type is a named qubit. Okay, so qubits in Cirq are just hashable and orderable objects. So one example of qubits is named qubit, which just says that you are defining a new qubit which has a name A. Okay, and these qubits have a default ordering in the sense that a qubit A would be less than qubit B if the name used to construct qubit A is lexicographically smaller than the name used to construct qubit B. Similarly, Cirq also has a concept of line qubits and grid qubits. So as an like we will also see it later in this workshop, but as the name suggests, a line qubit is basically a set of qubits on a straight line, indexed by their position on the line, and a grid qubit is a qubit on a 2D grid. So a grid qubit would be indexed by a x comma y pair on the grid. Okay, so as you can see now, here we have defined 3 qubits A, B, and C with the names A, B, and C. And then we have a list of operations that we would like to apply on these qubits. So in this list of operations, we first have circ.h, which represents the hadamard gate. Like some of you might be new to quantum computing, but if you attended yesterday's session by Microsoft, like they introduced what quantum gates are. So hadamard is a fairly common type of quantum gate, and circ.h represents the hadamard gate. And when you say circ.h of A, you are basically applying the hadamard gate on qubit A. Okay, so similarly, you have a list of operations that you would like to be in your circuit. So you have circ.hadamard or on qubit A, then again a hadamard on qubit B, and then a C0 gate on qubit B and C, and then another hadamard on qubit B. So to create a circuit from a list of operations, you can simply pass this list of operations to circ.circuit, and what you get out is basically a circuit object. If you print this circuit, you see a nice ASCII diagram. You should notice that this circuit has 3 different moments. In the first moment, you have a hadamard on both A and B. In the second moment, you have a C0 from B to C. And in the third moment, you have a single hadamard on qubit B. Okay, we will learn more about these insertion strategies. Like you should notice that the circ.circuit class took basically a list of operations, which is a 1D object, and turned it into a 2D representation. So it decided by itself that which operation should go into which moment, and we will see later on that how you can control this decision, like using something called an insertion strategy. Okay, so I hope that this gives you a good idea of how you can create your own circuits in Cirq. So now we have an exercise lined up for you all. You can see a diagram given in the exercise. So this is a diagram of a circuit. As you can see, like we want you to apply a hadamard on qubit 0, a hadamard on qubit 1, and then a C0 from qubit 1 to 2, C0 from qubit 0 to 3, and then another hadamard on qubit 1. The task is that we want you to create this circuit. Like we want you to write the code to create this circuit. So there are 2 blocks below. Like you can click on the first cell and it will expand. Like the cell will get expanded, and you should write your code to create this circuit in this cell. Okay, here we will take a break of a couple of minutes, and I would encourage everybody to go and try this exercise. And if you have any questions or if anything is not working, then please write in the comments and we will try to address it. Also, like the solution is given in the cell below, so I would encourage you to not open the solution and copy paste it in your attempt. Like just try to come up with the code yourself, and yeah. Okay, so do we have any questions in the comments so far?
Not from what I'm seeing about but they may come soon.
Yeah, I'm responding to questions as I see them in the chat.
Okay, that's good. So everybody who is able to complete this exercise, like I would encourage you to just write it in comments.
Some people completed it already.
Wow, that's great. So maybe we'll give another minute and then we will move on to the solution.
Awesome. 4, 5, 6 people.
So for those of you who are still trying this exercise, like I would maybe like to give you a hint. If you notice, we are using qubits which are indexed using integers. So we are using qubit 0, qubit 1, qubit 2, and qubit 3. You can either use named qubits to define these separately, or you can also try to use circ.line qubit to define these qubits. And also, like if you have already completed this exercise, I would encourage you to think about what these square brackets represent in this ASCII diagram. If somebody has an answer, it would be great if you can write it down in the comments.
So someone just showed that they used A, B, C, and D. That should be fine as well. It would be interesting to see like how you could make those ABCDs into 0, 1, 2, 3. Okay, and then we have some answers coming in for your question about those brackets. So someone said depth. Someone said that they are operations, and then two people said that they are a moment that represents a moment.
Okay, yeah, I think all these are very good ideas. Like maybe we should wait for another few seconds.
Independent C0 acting on two exclusive pairs is the same moment. So that means the same moment.
Yeah, so moving on, I think most of you are hinting towards the right answer. So if we expand the solution, we see that because you want 4 qubits which are numbered consecutively from 0 to 3, you can simply use this nice helper function in Cirq called circ.linequbit.range, and you can pass it a number n, and it will return you an array of n qubits which are indexed by 0. So q of 0 will be a qubit, will be a line qubit represented by 0 in the ASCII diagram. Q of 1 would be a line qubit represented by index 1, and so on and so forth. And once again, we want to define the list of operations. So first we have a hadamard acting on qubit 0 and 1. Then we have C0s acting on qubit 1 to 2 and 0 to 3. And then we also have another hadamard acting on qubit 2. And in the end, just like the previous example, we simply create the circuit by calling circ.circuit of ops, where ops is the list of operations that you want to pass to the circuit. Okay, and you print this circuit and you get this nice ASCII diagram. So now regarding the question that I asked, like what do these square brackets represent? So these square brackets basically represent a moment. This is just to indicate that despite the fact that these, like there are 2 separate vertical lines representing these 2 controlled operations, both of these controlled operations lie in the same moment. And to club these 2 operations together, we have this square bracket representation to represent moment number 2. Okay, so this circuit also has a total of 3 different moments. Okay, so this is great. Let's move on to the next topic for the day. So let's try to dig into the elements that we use to construct a circuit into slightly, like to understand them slightly better. Okay, so we first used this object called circ.h. So circ.h is like basically represents the hadamard gate. So the matrix for the hadamard gate is given by this like this text, which is basically 1 by √2 and then 1 in all positions except the bottom right position. Okay, so in the bottom right you have a -1 and you have 1 everywhere else. So this is the standard hadamard matrix. So circ.h in Cirq is basically an instance of circ.h power gate, and which itself is a subclass of the gate class. So in Cirq we have a generic gate class which can be extended to define like custom gates as well, or like all the gates which come naturally with Cirq also inherit from this gate class. Okay, so if you want to see the unitary matrix of any gate in Cirq, you can use this nice utility function called circ.unitary and pass it the name of the gate for which you want to see the unitary. So if you do circ.unitary of circ.h, what you get is basically a 2D matrix of the hadamard gate. Okay, and everybody should be able to recognize that this matrix is basically the same as the one given above, that it has 1/√2 at all positions except the bottom right where you have -1/√2. Okay, so this is a nice utility function, and the reason this works is that the gates in Cirq and also other objects implement a protocol called the unitary protocol, and we'll maybe learn more about this later on. But for now, like you can see that we have this nice functionality where you can call circ.unitary on objects and get back their unitary matrix representation. Okay. So in Cirq, we also have two different concepts. So we have a concept of a gate, and then we have a concept of an operation. So a gate is like a factory, which means that a gate just represents the actual quantum gate, but there is no concept of the what qubits does a gate act on. Okay, so a gate is like a factory which can act on a set of particular qubits, but when a gate is actually applied on a set of qubits, it produces an operation. So an operation is basically a gate which is acting on a set of qubits. Okay, and such an operation is called a gate operation. As I said earlier, there can also be other types of operations, but like this is important to keep in mind that circ.h is a gate, but circ.h of A is an operation. Okay, so it is an operation that acts on qubit A, and it applies gate circ.h on qubit A.
Sorry,
so you can simply, sorry, yeah.
Can you zoom in a little bit? Some people are
Sure.
having trouble seeing it.
So maybe I can.
That's great.
Is this better now? Or
Yes, much better.
okay, like is it still okay, or should I zoom in a bit more?
I think it looks good.
Okay, great. So yeah, so as I was saying that for gates, like to get an operation from a gate, you can basically either apply that gate on a set of qubits. So to do that, you can either pass the qubits to the constructor like this. So you can simply say circ.h of A, or you can explicitly call the on method and say that you want to apply circ.h on qubit A. Okay, and both of these will return you a gate operation, which can then be used in your circuit or your moments to create a circuit. Okay, so circuit would be a list of operations and not a list of gates, because of course, if you are just given a gate, you don't know what qubits does this gate act on. Okay, so once you have this set of operations or the list of operations, you can simply pass them to the constructor of the circuit to create an actual circuit. And we will learn more about how to create a circuit using different ways. But yeah, before that, like maybe let's unpack the circuit a little bit. So as we said earlier, that a circuit is nothing but a list of moments, and just like any other list in Python, you can iterate on a circuit. So you can iterate on all the moments that lie like that constitute a circuit. So in this example, like if you run this example, you will see that first you can print the whole circuit, which prints the same ASCII diagram. And then if you want to inspect the individual moments, you can simply iterate on every moment one by one, which lies inside this circuit. To iterate on moments, here I'm using this enumerate function for people who might be new to Python. Like enumerate basically lets you iterate on the actual elements along with, like it also attaches a counter, which means that it gives you an access to the index of the moment. So an enumerate of circuit will like if you just want to iterate on circuit, you will do for moment in circuit. But if you also want to get the index of the moment, you will do I comma moment in enumerate of circuit. Okay, so this will give you an extra counter which will represent what is the position of this moment in the list, which is underlying this circuit. Okay, so for example, in this case, if you try to inspect every individual moment, the first moment is moment 0, which has 2 hadamard gates applied on qubits A and B. Then we have moment 1, which has a single C0 gate applied from B to C. And in moment 2, we have a single hadamard applied on qubit B. Okay. So moving on, like we see that Cirq also has a nice utility. So in Cirq, for almost every object that we have in Cirq, we try to implement the wrapper method, and this wrapper method returns the actual code which can be used to create this object. Okay, so if you do print of wrapper of circuit, you will actually get the source code which you can copy and paste in a new Python cell, and this source code will end up creating the circuit object. Okay, and this is very useful. Like this is especially useful like for two different purposes. The first purpose is if you want to look under the hood and understand what is happening. So if you are new to Cirq, or if you want to understand how these classes work, or how like what exactly is happening under the hood, you can print the wrapper of any object and then see the exact code that can be used to generate it, like to generate this object. And I think the other most useful use case is while debugging. So if you have an object and you want to debug like some issue which is happening with this object, you can print the representation of the object and then copy paste this code into a new tab. So for example, if I copy it and if I paste it here, and if I run it, like this will create the exact same circuit which is represented by the circuit object above. Okay, so now like once you have this source code, you can make any changes you want and play around with it if you want to do any debugging. Okay, so all clear so far. Next, we move on to the different ways of creating circuits in Cirq. Okay, so circuits in Cirq are mutable objects, and that means that once you have created these circuits, you can also modify this like these objects to add more operations to the circuits. So the simplest way to create a new circuit is using the constructor, which we just saw, that you have a list of operations and then you simply pass that list of operations to the constructor of the circuit, and it will give you a new circuit object which you can then use in the rest of your program. Okay, but oftentimes, like if you are creating a circuit which is large enough, you often don't have the list of circuits available, like the list of operations available to you at the very beginning, and rather you want to keep modifying the circuit object as and when you want to append more operations to it. And to be able to do that, the circuit object also supports an append operation. So when you call circuit.append with a list of operations, this basically adds a list of operations at the end of the circuit. Okay, another use case could be that given a circuit, you want to insert some operation at a particular moment, and for that you can use the insert function. So you can do circuit.insert and then give a particular integer index which represents which particular moment, like in which particular moment do you want to insert an operation. Okay, so these are the different ways you can use to create new circuits. So now like one of the very useful facts about Cirq is that you can of course pass a list of operations to all of these functions, but you can also pass much more than just a list of functions. Okay, so you can basically pass a list of functions, or you can pass a generator function which sometimes yields a tuple of operations, or sometimes it yields individual operations, or basically you can pass anything which can be recursively flattened into a list of operations. Okay, so in Cirq we basically have this concept of an op tree, and an op tree is a contract which represents that anything which can be recursively flattened into a list of operations represents a valid op tree. Okay, and this is especially useful because, like, while creating large circuits, like you want your code to be modular, and like you want different functions or different generators that return you different types of operations that you want to insert in your Cirq, and you can very easily compose these different generators and list of operations to create like complex objects which are still valid op trees and which will be automatically flattened by Cirq when you pass them to any of the above functions. Okay, to look at an example of this, like we will create a circuit using generator functions. So if you look at this circuit basically implements a XOR swap operation. So what this means is that you are given two different qubits A and B, and you want to write a circuit such that when the circuit is executed, then the states of these two qubits are swapped. It doesn't matter what the state of qubit A is and what the state of qubit B is, but whatever that state is, it should be swapped once this circuit is executed. Okay, so this particular operation is called a swap operation, and it can easily be implemented on two qubits using three C0 operations. So if you want to swap the states of qubits A and qubit B, you can basically do a C0 from A to B, followed by a C0 from B to A, followed by another C0 from A to B. So if you add these three operations to your circuit, then the state of qubit A and qubit B will get swapped. And this is a utility function which is used many times as a as a standard operation that you want to do as part of a larger algorithm that you are writing. Okay, so we have this simple function which yields these three operations. Like for some of you who might be new to Python, like Python has this concept of generators, which are basically functions that yield like certain objects. And the good part about these generators is that you can iterate on them just like you can iterate on a normal list. So you can iterate on each of these operations one by one. So you see that like we can simply pass the XOR swap function to the circ.circuit object, and it will create this circuit for you. Okay, so now we have another exercise for all of you, and the exercise is as follows. We want you to implement a circuit such that when you run this circuit, like the circuit should left rotate 5 qubits. Okay, so like you have 5 qubits numbered from 0 to 4, and you want to run a circuit on these 5 qubits such that towards the end of this circuit, the states of the qubits are left rotated, which means that the state of qubit 0 should go to qubit 4, the state of qubit 4 should go to qubit 3, and so on and so forth. Okay, so maybe we'll take a break of another 2 minutes, and I will let you all attempt this this solution. Once again, like the template is the same. You have another cell where you can write your solution, and the cell is labeled as attempt the solution here. So please go and try to write a solution for this exercise. And if you have any doubts, please ask them in the comments.
Thank you, Tanuj. There's a lot of excitement around the octree and being able to pass in lists and lists of operations and lists of operations and things like that into the circuit. Yeah. Great. Let us know if you're done with the exercise.
Yeah, if anybody is done with the exercise, I would encourage you to please write it in the comments so that we can get an estimate. And if you are attempting it, but you're not yet done, then also please let us know so that we know that how many people are attempting the exercise.
One person done.
Okay, that's great. So how many of you are still trying?
There's at least one person who's trying and commented as well. There might be others. Okay, we got 2 done and 1 more trying. 2 more trying.
Okay.
So 3 people are still working at least.
So maybe we'll wait for a few more seconds, I guess, like maybe 30 more seconds, and then we move on.
Someone wrote that they are looking at the answer, which is also a possible thing to do because it's there. When it's done. It's like a quantum computer. You can't know the state. It's hidden until you measure it. Done.
Okay, so maybe I'll go ahead and measure the solution. Okay, so if you look at the solution, like you can define a function called left rotate, and this function would then yield this XOR swap function. Okay, so in a way, like we are composing these generators together. So we have this left rotate function which takes a list of qubits. It assumes that this is an array of qubits, and it simply iterates on all the qubits, and for every consecutive qubit at index I and I+1, it simply calls XOR swap for these two qubits. Okay, and then once you have, I mean, to define 5 qubits, you can once again use circ.lineQubit.range 5, and then you can simply create a circuit by calling this left rotate function on this array of 5 qubits. Okay, so this kind of demonstrates you the power of this concept of optree and how we can compose these different generators to come up with complex concepts where each of the individual functions or concepts like does one particular task. Okay, so it is especially useful to compose different generators together and write more complicated programs. Okay, and this would be the circuit that you end up with, which can basically left rotate your set of 5 qubits. Okay, great. And also like for some of you who might need the swap operation in their daily job or like while writing new circuits, like Cirq obviously has a circ.swap, which is predefined gate. Okay, like so we don't, like every time you need swap, we don't want you to write these 3 gates explicitly. Like this was just for demonstration. Okay, so moving on to the next part of this workshop, like we will now look at the different insertion strategies that exist, which can be used while creating new circuits. Okay, so we briefly talked about this earlier. Like as I said that, like while creating a circuit, you are basically passing a list of operations, and Cirq is trying to determine automatically that where it should insert a particular operation. Okay, so it is converting a one-dimensional list into a 2D structure, which has an ith index, which is the moment, and the actual operation that should be inserted into this moment. Okay, like so there are different insertion strategies which Cirq can follow. The default insertion strategy is the earliest strategy, and as the name sounds, it basically does the obvious thing that if you want to insert an operation at index I, it tries to find the earliest location backwards from index I where this operation can be inserted. And when I say that it tries to find the earliest position or moment where the operation can be inserted, it just means that like the earliest moment where there is no other operation affecting the same qubits on which a particular operation is getting applied. Okay, so like if we see an example of this earliest strategy, also the earliest strategy is the default strategy for all of these functions. So basically for circ.append, circ.insert, like circuit.append, circuit.insert, or just the constructor of the circuit, you have the default strategy as the earliest strategy. Okay, so for example, if you look at the example below, you first create an empty circuit, you append a CZ operation from qubit A to qubit B. So you insert this operation, and then you insert 3 more operations. So you append 3 more operations. The first one, a hadamard on A, a hadamard on B, and then a hadamard on C. Okay, so for hadamard on A and hadamard on B, it cannot go and insert it into moment 1 because in moment 1 you already have a CZ operation. Okay, so what it does is that it tries to find the earliest moment in which it can insert these operations. So the earliest moment is moment number 2, or like moment number 1 if you look at zero-based indexing. So it inserts a hadamard on the first moment for A and B. But for qubit C, if you want to do an hadamard on C, you can actually go on moment 0 and insert it there because that is the earliest moment because where you can insert a new operation for this qubit. Okay, so it inserts it on moment 0 instead of inserting on moment 1, despite the fact that this list was passed together. Okay, so to summarize, like the earlier strategy basically tries to minimize the depth of your circuit. Okay, in some sense, it tries to minimize the depth of your circuit by greedily finding the first, like the earliest index at which it can insert a new operation, and then just going and inserting it at that index. Okay. So apart from that, we also have other strategies. For example, we have a new strategy, which is not very useful because like this strategy basically just inserts every operation into a new moment. Okay. So similarly, we have an inline strategy, but probably the next most useful insertion strategy is new then inline. So it, like the new then inline insertion strategy is helpful when you want to think about building your circuit moment by moment. So what this means is that every time you call a insert function or an append function with a list of operations, like for the first operation, it basically inserts the operation into a new moment, like into a new moment at the insertion point. And for every other operation following the first operation, it tries to insert that operation just before the desired location. And if it's not possible, then it creates a new moment and then again tries to insert that operation in this new moment. Okay? Like the new moment becomes now the position where the subsequent insertions will happen. Okay. So maybe it is easiest to understand this strategy using another example. So if you come down and run this cell, like you will see like another example. So once again, like the list of operations that we are passing is the same as above. So once again, we are defining a new circuit, which is an empty circuit, and appending a list of operations. In the first append, we only insert circ.cz in A and B. And in the next append, we insert circ.h on A, B, and C. So we insert in hadamard on both A, B, like on all three A, B, and C. But the insertion strategy that we use this time is new then inline. So we use circ.insertion strategy dot new then inline specifies this insertion strategy. Okay. So when you use this strategy, you see that this time the hadamard on C got inserted in the first moment instead of the 0 moment, because for new then inline, it creates a new moment for the first operation, and then for every subsequent operations, it tries to insert these operations in this moment that it has created. And if it's not possible, then it creates another new moment and keeps doing that. Okay. So hope this gives you a good idea of the different insertion strategies available in Cirq. We have one more exercise lined up for you, but I see that we are slightly running we are running slightly late. So I would like to do a time check and see whether we have a time for this exercise, or like maybe we should move on to the last topic of the day, which is simulations. Like the last topic for this hour, which is simulations. So, I mean, do you think we have time for an exercise, or?
You have 2 minutes to the hour mark, but you're blocked until 4 my time. So you have basically an hour and maybe 15, 20 minutes if you want it.
Okay, so like I guess we will move on to the next topic, because after me, like Valent will also continue the second half of this workshop. So like I would encourage everybody to attempt this exercise yourself. Like this is an especially interesting one because it asks you to create this circuit with the least number of appends, and yeah, like it is self-explanatory. You can look at the solution later on, but right now I will move on to the next topic for the day, which is simulations of a circuit. Okay. So far we have learned how to create circuits, but once you have a circuit, you would also likely want to simulate it. So in Cirq, like we have a concept of a simulator. So for example, in this first cell, like this is a basic, like once again, we are basically trying to create a circuit. So we have this like generator function which yields some operations, and we pass it to the circ.circuit object to create a new circuit. Okay. But now we also have a concept of measurement. Like so far we haven't looked at any circuit which contains measurement gates. Like Cirq has this utility function called circ.measure, in which you can pass a list of qubits, and it will return you a measurement gate on all these qubits. Okay, and by default, the measurement in Cirq happens in computational basis. If you want to do measurement in any other basis, then you would likely want have to do some do the necessary rotations and then do the measurement in the computation basis. Okay, so the measurement gates in Cirq by default measure in the computation basis. So if you print this circuit, you can see that like you have a circuit on 2 qubits A and B, where you first apply a square root of X gate, like then a CZ gate on AB, and then again a square root X gate on both A and B. And in the end, you do a measurement on both A and B qubits. Okay, so you have this circuit, and to simulate this circuit, like you first create a simulator object. So the general pattern is the general pattern of simulation is to first instantiate a circ.simulator object, which will give you a particular type of simulator. Now Cirq has different types of simulators. Like one is the wave function simulator, and another is, say, the density matrix simulator. Cirq also has a good interface with like many other high performance simulators, for example QSIM. Okay, so you can use any of these simulators to first create a simulator object, and once you have a simulator object, you can pass your circuit to it to basically simulate your circuit. Okay, so now like in the simulator, there are also two different concepts. Like there's a concept of run and there's a concept of simulate. Okay, so when you call simulator.run, it basically tries to mimic the actual quantum hardware. What this means is that this will not give you access to the underlying wave function, but it will simulate this circuit, and then in the end, if there are measurement gates, then it will do the necessary measurements and give you the measurement results back as the result object. Okay, so in this case, for example, like I call simulator.run on this circuit, and the run method also takes a bunch of like another parameter called repetitions, because so this is useful to specify how many different times do you want to sample from this circuit. Like if you only sample one time, like you can see that you only get a single result in the result. Like if you sample multiple times, then you can get like multiple different results for every time, like for every sample that you want. Okay, so like for this particular circuit, I mean, this circuit creates an equal superposition across all states. So therefore, like running this multiple times like should likely result in different results, because if you are sampling from a circuit which is in superposition, like you will likely get different results every time. Okay, and similarly, you also have the concept of simulate. So what simulate function does is that it basically like helps you understand what exactly is happening in the circuit. So basically, it can give you access to the underlying wave function. So for example, in this case, we create a new circuit, but this time we don't add measurement gates so that the underlying wave function does not collapse due to measurement. And for this particular circuit, we pass it to the simulator.simulate method, and we get a result. So on this result, we can actually print the final state vector, and we can also print the Dirac notation of the final state vector. So you can see that, like for the circuit which was constructed using this basic circuit method, the circuit, like the final wave function before measurement is actually in a superposition, like is actually in an equal superposition of all the four states. Okay, so like if you want to artificially simulate a circuit and understand like the actual wave function, like look at the actual wave function, you can use the simulator.simulate method and print the Dirac notation of the final result. Okay, like there's also a concept of qubit ordering. So by default, the ordering of the qubits would be the same as the lexicographic, like would be the same as the natural ordering among the qubit objects. Like as I said earlier, every qubit is hashable and orderable. So for named qubits, like the ordering would just be a lexicographic ordering of these qubits. And the reason we need qubit ordering is because this defines the ordering of the tensor products that would happen, like that would occur in the final wave function. Okay, so for example, if I swap this to b comma a, and run it again, like you will see that the states actually got swapped. Okay. So the qubit ordering basically controls that in the final wave function, like what should be the ordering of qubits in the tensor products. Okay. Okay. So now, moving on to the last topic. Oftentimes, like when you create a new circuit and when you simulate this circuit using the run method, which mimics the hardware, you have multiple repetitions. Like you want to simulate the circuit like for multiple repetitions, and then like for the given final result, you want to print the histogram of the different results that were observed during the different repetitions. Okay. So for example, like for this particular circuit, if I run it in the simulator for 1,000 repetitions and I get a result, I want an ability to process this result and look at the histograms of every output. So we have a convenient function on this result. So you can directly call result.histogram and you can pass the measurement keys. So like for measurements, as I said earlier, that like measurements have a concept of keys which are assigned to every measurement. By default, the name of the qubit becomes the key of that particular qubit. Okay. So like in this case, for example, like when you pass the list of keys to the histogram, it generates these numbers from the actual qubit ordering. So when A is 0 and B is 0, the final number is 0. Like when A is 0 and B is 1, the final number is 1, and so on and so forth. So it converts a list of qubits to binary numbers, and for each of these numbers, it gives you like the histogram of how many times this particular result was observed during all the repetitions. Okay, so like in this case, you can see that for 1,000 repetitions, 2 was observed 279 times, 1 was observed 249 times, and so on and so forth. So like all of them are observed roughly equal times because the circuit was in a equal superposition. Okay, and if you want to process these results, you can also pass another lambda function. Like in this histogram, there's also a concept of a fold function which can be used to basically process these results the way you want them to. So for example, in this case, like I'm passing a lambda function which takes the list of bits and it returns an agree if the bits are same. Otherwise, it returns disagree. So basically, for 0, 0 and 1, 1, it would return agree, and for 0, 1 and 1, 0, it would return disagree. So you can count that how many times how many times in the result are both the bits same, and how many times in the result are both the bits different. Okay, so you can have a histogram of that as well. Okay, so I think I have reached the end of my section. If there are any questions in the comments, I'll be happy to address them, or else maybe we'll take a couple of minutes of break and then Balint can take over with the next section of the talk.
There was one question about can we give us a practical example where it's more advantageous to use the new than inline strategy over the default one? And yeah, because the default is the earliest, and then new than inline, when is it that more advantageous?
Yeah, so one use case is basically that when you are constructing new circuits, you are basically if you are thinking of constructing a circuit as adding operations moment by moment, and you have a you have in your mind that at different points of time, you have in your mind that okay, so far I have 10 moments with a particular structure, and then I want to add say a few more operations and create a few more moments after it. So you don't want the existing first 10 moments to get impacted by new operations that you want to insert. Then in this case, for example, you would want to use the new than inline strategy instead of say the earlier strategy. So it basically ensures that all the new operations are applied on everything that all new operations are applied after everything that already exists in the circuit. So it doesn't change anything that already exists.
So there's a follow-up question, but how is that going to influence the final state? And how does it affect the depth of the circuit?
Yeah, so like it would not impact the final state, but it can it can increase the depth of your circuit at some point. But like oftentimes, like for example, like many times, minimizing the depth of the circuit is not the only goal. Like sometimes, for example, you also want to push all the measurement operations to the end because you don't want to do measurements at different points in time. Like oftentimes experimentalists would want to do measurements all at once at the same point in the end. So in this case, like you would want to right align all your measurement operations, for example. So like for different use cases, like minimizing the depth might not be the only thing that you want to optimize for. And similarly, like if for example, like during while creating new circuits, if the idea is that like you want to ensure that new operations don't impact anything existing, then in this case, like you would want to use the new then inline strategy.
Yeah, another example is where depth is not necessarily the goal. Is in our devices, you want to align 2 qubit gates together and single qubit gates together and then alternate with them. So even if you could like push them next to each other, 2 qubit gates are actually running faster than 1 qubit gates in Google devices. You would have on the 1 qubit gates, those qubits idling until the 2 qubit gates are being executed. So that leaves you with unutilized qubits. So you want to actually like organize in a way your circuit that you stratify 2 qubit gates and single qubit gates together.
Excellent. So if I guess if there are not any other questions, we can take maybe a 5-minute break and then go to balance section. Excellent. So yeah.
Sounds good.
Sounds good.
Take a break and then reconvene. See y'all in 5.
Sure. Thanks everyone for the attention. Yeah. See you all in 5 minutes.
5 minutes. Thanks so much.